Right. Hey, everybody. So in this video, we are going to introduce one of the major topics in real analysis, and that topic is about the limit of a function. Now, you know this name, right? Limits were a big thing that we studied in Calculus 1, and so it is exciting to see them appear here again in real analysis. So I want to start, before I even introduce the formal definition of a limit of a function, I want to first suggest that this new definition is nothing more than the latest definition, and maybe the most complicated definition, in what has really been a set of several similar definitions that we've seen in real analysis. Let me explain. When I think about the definition of a limit, I see it as being maybe the sort of older sibling to the definitions of an accumulation point of a set. Right? On the one hand, and the limit of a sequence, or the convergence of a sequence, on the other hand. Right? Both of these definitions, much like we will see the definition of the limit of a function, deal with questions of behavior in a sort of infinitely close or arbitrarily close manner, right? And we see that these two definitions are relatively similar to each other. If we want to say that a point P is an accumulation point of the set S, we are really saying that elements of S are arbitrarily close to P. And we have that sort of arbitrary closeness. We have that in this epsilon definition. So we said for all epsilon, the set that included the deleted epsilon neighborhood of P and the set S, that set was not empty. Or in other words, within any deleted epsilon neighborhood of our point P, we can still find points of S in there. Now, convergence of a sequence is actually a very similar definition. It's saying that a sequence gets arbitrarily close to a limit L. And so if we were saying, right, notationally, we would say the limit as n goes to infinity of our sequence A sub n equal to L. Well, by definition, what we're really saying is that our sequence gets arbitrarily close and stays arbitrarily close to L. And so that's like saying for all epsilon, there existed some value beyond which elements in our sequence would be within the epsilon neighborhood of L. So for all epsilon, there exists an n such that if little n is bigger than big N, A sub little n would be within an epsilon distance of L. Okay. And so I'm just, my purpose in bringing these up is just to point to the similarities in these definitions, the idea that they're both dealing with sort of behavior as we get arbitrarily close to a given value, and to set the stage for our definition for limits of functions. So, with all that being said, let's take a look at three equivalent definitions. And all of these definitions are trying to summarize the idea of what it means for our function to approach a limiting value of a height L as our input values get really close to the height P. So notationally, we will use this notation that you know and love from Calc 1. And what we're saying here, let me move this. See, so we will always start with the setup in which we have a function from some domain into the real numbers. We have a point P that we'll be talking about. This is an accumulation point of the domain. It's possibly in the domain, but at least it's an accumulation point of the domain as a set. We will then say that our function has a limit at P, has a limit L at P, if and only if, now maybe I'll again highlight, because this is going to be the meat of the definition, for all epsilon there exists not an n, but in this case, a delta. So for all epsilon, there exists a delta such that whenever we have an x value that is in our domain and within distance delta of p, we have that our function values, our output values, must be within distance epsilon of L. So in this definition, we are trying to capture this idea of closeness. We expect our function at a point P to have a limit that approaches a height L. We expect that to mean that as we get closer and closer to our point P, our function's height values will get closer and closer to a height of L, right? And so we're capturing this by saying that for a distance epsilon, we can guarantee that our function values will be within distance epsilon if we can make our input values within distance delta for our point P. Now, there are two equivalent definitions that we have written down here, which are really just rephrasings. So these are going to have the same main definition. These are going to have the same, these are going to have the same assumptions. So we're still going to have a function f from D to R, and we will let P be an accumulation point. We say that a function f has a limit point at P if and only if. So here's the rephrasing. For all epsilon, there exists a delta such that whenever x is within this intersection, the intersection of the domain and the deleted delta neighborhood, and I should really specify that should be the deleted delta neighborhood of P, we have that f of x will be within the epsilon neighborhood of L. All right, definition one. Definition two, again, equivalent definition two, we say that a function f has a limit L at P if and only if for all epsilon there exists a delta such that the image of the set that's given right here, so deleted delta neighborhood of P intersect D, if and only if the image of that set is a subset of the epsilon neighborhood of L. So if I wanted to write that using my set notation, we have the image, right? So that would be f of n d star P intersect D. So that image as a set would be a subset of n epsilon sub L. Okay, let's cut to a picture to sort of explain this definition in slightly more detail.